Hi there, Matt Heffernan. Welcome back to my channel. A little more hand modeling today. Nope, you know what that means. It's actually another unboxing. And this time, contrary to earlier occasions, I did not buy something from Wish. I bought it from an actual reputable retailer and not Amazon, because Amazon doesn't really cover stuff like this. This, of course, is from Mouser. And you might be able to guess what this is. The box is a little bigger than it needs to be. But it is, well, let's see. Let's see what it is. What can I get from Mouser? You might remember, and I opened up and tried to use that FPGA board. I couldn't quite get it to connect to my computer. So, I think the problem with that was the USB blaster that came with it, and that's what this should be. Let's see. Let's see if it actually comes up, because it does say on there Thoracic USB blaster. And Mouser, unlike say Wish or AliExpress, they don't generally sell counterfeit goods. I'm not saying that they don't ever do it, especially with supply chains the way they are now, but generally you can trust them. But this is going to be a genuine thoracic part. All right, so here's USB cable. It's like a printer style cable instead of the mini USB. I forgot the other one. And oh, look at that. There we go. That looks like a real USB blaster with our little JTAG slash serial type connector. It definitely looks real. It looks a lot more real than the fake Altera one that came with the FPGA board. So what we're going to do is try to hook this up to that board and see if we can really connect to it finally. All right, so we're back again. We've got now the new official USB blaster connected, and we are, rather than connected to Linux, unfortunately, yeah, we're on Windows. Even with the real with the real blaster, it does not want to connect to Linux without doing those UDEV changes. That's okay. I'm going to try that another time, because I am determined now to get this toolchain to work on Linux. But Windows, as usual, is just kind of the easy mode. So here we are back again with this LED program. It's going to turn them all on. 0 means on. And I'm going to turn on. And we can see here the output LEDs are in that flashing pattern that they're on, because the EEPROM on the board is programmed with this little blink and light demo. It doesn't it doesn't save anything other than that, because I have yet to actually burn something onto the EEPROM, so it's always going to boot up to this. What I want to do is now just make them turn all on with this program that is all set. So what I will do is bring up the programmer, and now you can see it recognizes a USB blaster on there. If I click hardware setup, we'll see there it is, USB blaster. Sometimes it says it's alternative, but it kind of figured it out. And when I have it turned on and I do an auto detect, yep, it's there, and says, yep, we can load up this SOF. So the SOF file is, when you do it over JTAG, will just write to the RAM. It's not going to write to the EEPROM, so that it's only going to run this image while we're still powered on. So we'll go ahead and click start, and it says 100% successful, and look at that. It's so quick. There they are. They're all turned on. Amazing. So let's go back to Windows. Yeah, we'll save that. Now we'll say, all right, let's turn off, or actually, how about we'll turn on only one of them. So we'll make these 111. We'll save that. We'll hit the compile up here, and then we'll wait for the compilation to finish. It's about 75.99 and 100%. All right. So we're good to go. Here, as you can see, the board still running the last program. That's off of RAM. We click on the program. Now it's still going to be the same file name. We hit start on that, and it's going to write it, and look at that. Immediately. I know it's kind of hard to tell. There's a lot of glare there, but yeah, only that rightmost LED is actually turned on now. So yeah, the tool chain is working. Ladies and gentlemen, this is a real FPGA. It's a real Altera, at least functional FPGA, and I can program it, at least with a program this small and simple. So next step is going to be doing something a lot more complicated than this. So figured out how to get it to work on Linux too. So what I had shown before in my first video was an example of how to set up your USB rules on Linux. So what you're going to need to do, at least for most distributions, is go to your user lib udev rules.d directory. And in there, you're going to need to create a new rules file. And it's going to need to start with a 92, and we'll call it 92-usbblaster.rules. And this is what you're going to need to put in there. So at least for the hardware that I have, I need the original USB blaster configuration. So I have these 3 lines at the top that allows everything to operate in that 666 mode so that it's readable and writable by all users and groups on the system. And then if I had a USB Blaster 2, which you'd use with a newer dev board, I'd have that set up the same way also, so that it covers the full span of product IDs that we'd expect to see for one of these compatible USB Blaster cables. So let's get out of here and take a look now back in Quartus like we had seen before. Here we have that same weird example code that I'd seen before that just turns those LEDs on. And now I can go here into the Linux programmer. So now if I do an auto detect, it actually sees it. So things are actually working now. And I can do a start, and it programs. You can see it programs very quickly, and now I can see all the LEDs turned on just as I saw before on Windows. And I can do the same thing as I did before and make it so just that one on the right is turned on, and I can compile. Let's see how much faster this guy is. It's probably a lot faster. So there we go. It's all working, and we'll go back and reprogram that. And now again, still see just the one LED set. So full tool chain is working in Linux, and yeah, we're all good. So I think we're going to be having a lot of cool things happening now with this.
3 days later.
So as we saw when we unboxed it, we have these 7-segment displays on there, actually a bank of 4 of them, and really it's not just 7 segments, they're really technically 8-segment displays for this digit tube appliance that's on the board, because you do have these little decimal points there for the 8th segment. And of course, no documentation about how this is supposed to work at all. So this is the first bit of Verilog HDL that I went and created something from scratch, and had to reverse engineer how this dev board is wired and operates. So what I found was this, I created this little diagram here to show what the different bits, the different data lines map to for the 8-segment display for each digit. And then that we have these 4 select lines labeled dig for digit, and basically whichever of these 4 select lines are held low, that's going to be which actual segment is going to get these the segment lines here, these 8 segment lines. That's going to determine which of the segments for that digit are going to be displayed, are going to be lit up. And I'm using the clock too because I've got to time things out, as you'll see, because what we're actually going to do with these 4 digits is have a decimal counter so that it goes from 0 through 9,999 and then rolls back over and just keeps going up. And then here I define parameters for the different patterns that I want to be able to write out to a segment up here. And so I have patterns for 0 through 9. And then I went ahead and did A through F2 because I'm going to be dealing with 4-bit values. And those 4-bit values, in case things aren't going properly within the decimal realm, may get up into the hexadecimal realm. So I went ahead and made these lettered patterns too for A through F, just in case I'm putting out the incorrect pattern, not doing the decimal count correctly. And also it helped for debug. And initially just making the counter a binary counter, of course, is a lot simpler. We're dealing with we're dealing with a Boolean logic here with the actual digital electronics, and binary is what it wants to do. So I did have it work as a hex counter for the first run. One of the things I'm going to need to do is every time I select a new segment, I need to say here for this current segment, I have a 4-bit value, and it's going to be from 0 through F, potentially, in hex. And then, then here's where I have that mapping from that 4-bit value to this 8-bit segment pattern. So that makes that very simple. And then I have another mapping here for digit select, where then the selected pattern is going to be that counter digit based on the 2-bit thing. So here we're mapping 2 bits, a 2-bit select value to a 4-bit data value. Going through and saying, all right, I'm putting out digit 0, putting out digit 1, digit 2, digit 3, then back to 0 every time I go through that, because you can see here I have a counter where I'm just incrementing that value. And then that just effectively gets rolled out into these 4 separate select lines. So based on the states of the 2 bits in this value, it's going to then hold the appropriate digit select line low. Now here I'm doing the counter, the big counter. So every 50 megahertz clock cycle, I am incrementing our counter, and so that's going to be that 24-bit value. When we hit that positive edge on bit 15, then we are going to select a different digit, and then when that 23rd bit is selected, so that's our that's going to be our actual decimal counter period. I go through and see, hey, is digit 0 already at 9? And if it is at 9, then I'm resetting it to 0, and then making sure that is getting carried up into the next digit. So if digit 1 is 9, then that goes to 0. And then if digit 2 is 9, that also goes to 0. And then if digit 3 is also 9, then that will go to 0 as well. And that's our rollover that will happen. And then, of course, all these else statements where we're just incrementing each of those digits. And that's it. That's all it takes to do a decimal counter. So, I mean, really simple. This is pretty much what the logic that you would have in a digital stopwatch. And here I can have it very much customized to the exact timing that I'd want for it. So, of course, though, I am really limited by these tubes. They they have to be operated at a pretty slow rate to be effective. But as you're going to see, it comes out pretty nice. So here we see our board is back at its default state, doing the little blinking light demo. And then we can see, here's our code in Quartus. We bring up our programmer, and we just click start, and it's not going to take long to get that to run, and boom, we're already off to the races. And look, it's a decimal counter. And you can see again, those other LEDs are just shut off. This LED over here is just power, so that's going to be on no matter what. It doesn't look like I could control that one, but as you can see here, we'll let it roll up into the third digit. That it's all working pretty good here, and we have a much more useful sort of immediate feedback on the board than these 4 little LEDs down here. So there we go. There's a third digit, but again, I can explore a bit more of some of the other hardware we have on there. We have this guy right here, who's a little buzzer, kind of like how you have on a ZX Spectrum, just a real simple buzzer. And then you can guess what I've got over here. Yep, this is a VGA cable, and here is the VGA port on there, and we're going to take a look at now how some of these other peripherals work. Some of the other peripherals are going to have to wait, because what we do also have over here are the PS2 port, and I'm going to have a keyboard that's going to go in there, and then this is a RS-232 serial type port that is connected to a UART chip that is here. So even though the VGA interface may be a bit limited, as we're going to see, that with the UART we can connect it to a terminal, or at least a terminal emulating program, and then use this as more of an old-fashioned computer that you had to hook up a terminal to. So let's see now how we can get a little bit of actual audio video coming out of this thing. So here we can see a much simpler program, and as you can tell by the illegible writing, that it still has those Chinese comments on there. I have tried to actually translate now some of this, and it looks like it's just nonsense. Even though in Atom I can change the encoding so that it is the actual native encoding of these documents, because these aren't Unicode, it's a special Chinese encoding, and putting that into Google Translate, and it just comes back with sort of it doesn't come back with a translation. It just says, well, this is what these characters mean, and the characters are also tend to be very repetitive, so it's really not clear like what they're actually saying. If this is supposed to be maybe some sort of English that's been like phonetically changed into Chinese characters, I don't know what's going on with these comments, but you can see things like beep sort of poking through, and that's what this module does. It just uses the little beeper, and similar to how we saw in my counter demo, this demo also it does a big binary counter, and every clock cycle it goes ahead and increments. Here this is a 28-bit counter, and then what it does is it actually looks at 4 of those bits in there to determine when it's going to beep. And I do believe that this beep output, again, you've got to hold it low to make it make a sound. And it sounds like what it does is here, when that 9-bit is set, it will do a beep if the bits 13, 24, and 27 are all set. So by having bit 27 set, then that means that it's half the time that this thing is going to operate. So that will definitely make sure that it's going to be cutting down the cycles of beeps by quite a lot. Haven't done all the math as to what exactly this figures out, but as you can guess, by having these 3 bits set, it's going to create a little pattern of beeps. So let's take a little listen to what that's going to look like. All right, so again, we're back to the default state for the board, and then here in Quartus, we're going to go ahead and do the programming of this beep program and listen. So yeah, it's like a 4 beep pattern. So yeah, it seems to be going through this 24, or rather 20, this 28-bit counter, and it goes through, and seems like each half cycle it does these 4 beeps. So yeah, it just seems to be the same frequency. I don't know if this is going to work the same as, say, the Spectrum beeper, but I'm guessing you could probably get a little fancier with this and maybe try to make this beeper do different frequencies by sort of hitting it a little harder. But we'll see. Anyway, so audio is taken care of. That's what we got for audio. And of course, we can always generate like bells out of the serial connection here. But now the big puppy is, what kind of video can we get directly out of this thing? You might notice up here, let me shut this off. Right up here, you see this thing there. It says LCD. And this here is a connection for an accessory board that has a little TFT display that you can just plug right in there. And there's also built-in demos in this little repository that can activate that, and actually uses the DRAM chip on here to act as video memory for this display. Now, that I'm sure you could do something really good with that, and the fact that you have all these outputs. But as we're going to see, the output that's on this direct connection right here is definitely a lot more limited. So this demo right here, this is the last one we're going to do. This will actually use that VGA port, and it is based on a demo that again came with this repo, but I've switched it up a bit to make it work a little more interestingly, to better show how things can perform with this with this weird little board. So you'll notice here that it takes in the clock like the other one. Then it has these switch inputs. Those are those little momentary switches that are on the board next to those 4 LEDs. There's 4 switches, but it's using 2 of them. And then it has the actual outputs for the VGA port. And it has 1 bit for each of the R, G, and B signals for the video itself, and then the H sync and V sync signals, the horizontal sync, vertical sync signals, so that it knows when to actually say, hey, this is a VGA signal, and this is how long I'm going to be every H sync. This is going to be the beginning of a line of video data, and then at that V sync is like, oh, here's the beginning of a frame. So that's how a VGA monitor works. Is it's looking for at least these 2 signal values, and then taking as it goes sweeping across the screen from one H sync to another. The frequency of the H syncs helps it know like how long it's going to take to scan across, and then you're just changing these what are actually analog values for red, green, and blue that are going to be displayed. Now, as you can probably figure out at this point, is since this is a digital output, we basically only have on or off for our red, green, and blue components of video. So we're going to have a whopping color depth of 8 colors. And they're all going to be the same intensity. And that intensity, as we're going to see, is not great. But anyway, and then here we see more parameters for the timing that we're going to use. So now we're dealing with this 50 megahertz clock, and we're going to be deriving a VGA clock from that. And if we skip ahead a bit, we can see here what we're doing is at every positive edge of that 50 megahertz clock, we are just inverting the state of the VGA clock. So we're effectively doing a divide by 2. So we're going to have a 25 megahertz VGA clock. And then up here by these parameters are saying, all right, at 95 VGA clock ticks into there of each scan line, we're going to turn off that H-sync signal. And then at we're going to say from 95 to 143 is going to be the front porch. That's the time the scan line that's happening before the anything's going to actually be visible. And then we're going to say, all right, then the data is going to end there exactly 640 ticks later. And then effectively we're going to have 800 ticks because each pixel end, the back porch will end, and we'll start a new H-sync after that 800th tick for each line. So we're going to have 800 of those 25 megahertz ticks. And then for the V-sync, we're just counting up all the different H-syncs. So for that one H-sync period, we're going to have that V-sync signal on. And then we're going to say that 34 lines down is the end of vertical blanking, and then we'll have 480 lines of video, and then after that another 10 lines of vertical blanking after the end, after the bottom of the screen. So that VSync, you can see, will happen in the middle of all that, in the middle of that vertical blanking section of the display signal. So that's going to be enough to get us a 640 by 480 VGA signal going out on this port. But because it's the RGB signals are digital, it's going to be either on or off for those at whatever the intensity is that it puts out. So generally, you're going from like 0 to 0.7 volts on one of these analog RGB signals, and I'm guessing it's significantly below 0.7 volts because otherwise I'd expect a lot more brightness. But then also with this timing, it's going to work out that by doing 525 rows of, or basically 525 times 800, because we're doing 525 lines that are going to be 800 ticks each, and that 25 megahertz VGA clock, that's going to get us pretty close to a 60 hertz refresh rate. It's about 59.5 something. So again, we're dealing with our source clock signal at 50 megahertz. So we can't just like divide. There's not an easy number to divide by to get that down to 60 hertz exactly. So we're getting reasonably close to 60 hertz here. What this original demo did was this. It said that if every VGA clock, it would take a look at that line count the horizontal line count and say, how far along on the line were you? Well, then we're going to have this vertical color be set to this value, and then we'll do the same thing with this horizontal value. So we're defining color columns and then horizontal color rows here based on, again, these timings within that, so that we have these sort of even bars. You can see here horizontally we're going 80. So this is like 80 pixels wide, 80 out of that 640, so that we'll have those 8 bars going across. And then here having going 60 each way, so 60 pixels high, going down for 480. So again, eight rows of these big thick bars that we can do. And then depending on the switch states, if there's no switches, it's going to do an XNOR, exclusive NOR of the vertical color and the horizontal color, which should give us a nice checkerboard pattern of all these colors. But then here, if switch 1, I've kept this, I kind of switched things around a bit, so I made switch 1 just show those horizontal bar colors. Switch 2, as it was originally, it will show you those vertical bar colors. But then I changed, if you have both switch 1 and 2 held down, then it's going to do this sort of quasi VRAM thing, where here I've defined this very small section of VRAM. It's a 3-bit VRAM with these 8 3-bit values that are in it. And I just made the index the same as the index or the address, technically, of the VRAM to be the same as its value. But these could be any arbitrary values in here. And so I made it so that it would then get that that current color value. It would subtract that begin count from the H count, so that we would start with color 0, and then I'm shifting that by 1, so that what effectively I'm going to do is treat this VRAM like these first 8 pixels are going to be sort of doubled up, so that we're dealing with a 320 by 240 scaled display within this 640 by 480 signal that we're putting out. And then here I do this addition of the V count, which will end up creating these diagonal lines. So we'll see the full 320 by 240 resolution, and each scan line are going to have the colors shifted by one of these chunky pixels. So let's just see what this is actually going to look like. All right, so we're back again to the default state, and we're connected to this monitor right here at VGA. But as you can see, my favorite YouTube channel, and hopefully yours too. And you know what? Look, we got some awesome buttons here. In case you hadn't noticed, there's going to be a join button on there. If it wasn't me, there'd also be a subscribe button. Try to click that subscribe button, and then there's going to be a little bell next to that too. Click that too if you haven't. And if you want to support the channel, you can click the join, or you can, of course, go into the about section. And I've got all these links to social media, including the Patreon, if you want to support me there. And we'll see some more on that later. But first, what we're going to do is program our board. So let's bring out the programmer. We're going to do it. So that's all programmed, and you notice here little blinking lights stopped, but we're still connected to my quasi-modern desktop computer on here. So let's I'll switch here to my VGA signal, and there we go. there is our beautiful VGA signal that is put out by this guy right here. But you might notice that that white ain't quite so white. It is definitely sort of like the brightness turned off mode of the ZX Spectrum. That's sort of the color intensities that we're getting here. So it ends up being more of a light gray for the white. Now here, if I push this button down, you see it switches to the horizontal bars. And I let it go and it goes back. I hit button number 2, and there we go. Now it's the vertical bars. So horizontal, vertical, and now I hit both of these guys. If I can get my finger on both of them, and now we can see, ooh, we'll have to zoom in on there. Now you can see these nice chunky pixels, and you'll notice they're a little rectangular because here we're dealing with 320 by 240, but on a modernly proportioned screen. So yeah, those pixels are going to be stretched out a bit horizontally. But that's what we can sort of expect. And to get sort of a Commodore 64 type look on it, here, let me go back again. We can expect to see, 8 by 8 tiles of this could have characters. So we could do a character generator with this, but we are going to be stuck with just this is your palette. You're not going to have any additional colors than this. Even though you're on VGA, there's not going to be 16 color, much less 256 color. But again, we have this connection here, and the way this is mapped with its normal daughter board is that it uses multiple bits to determine each of the color channels. I think 4 or 5, depending on whether it's RG or B. And that will get us a lot closer. It doesn't give us 24-bit color, but it gives us something like 12-bit color, kind of like the Commander X16. So we can try playing with that. That ultimately we aren't forced to use this. It is kind of nice that this is a single board computer potentially, and that we could just hook the monitor directly up to this built-in thing. But what's going to get us better results generally is going through the UART, which we'll look at in a later video, or using these additional outputs and then effectively giving this thing a video card. Now that video card wouldn't be anything, have to be anything more sophisticated than another VGA port like this, or maybe DVI or whatever, and then having multiple bits for the different color channels coming out of this interface right here. So we'd still have the horizontal and vertical sync, but we can use all the rest of the pins for probably, of course, power and ground too. And then the rest of the remaining pins, we can get a little more color depth and just have a little digital to analog converter on there that will give us the voltage levels that we're looking for. Again, that 0 to 0.7 volts on RG and B to determine our intensity. And so I think that's something that is fairly easy to do. Is it something that I'd want to do in a project like this? I'd really much rather have, if I'm going to create a single board computer that runs on this weird little board here, that I really want to stick to what is available off the shelf. And they do have that TFT off the shelf. That could be one thing to use, and just either use the TFT, use the built-in VGA with the 8-color palette, and then or use strictly the UART and connect it to like a VT400 terminal. So those are the options that we're going to have for doing this. But so far, everything that I've tried to do with this that would appear to be within the bounds of everything being real, it's all worked out. So hopefully what we'll see in the next video is testing the PS2 and the UART, making sure those are working, And especially with the UART, things become a lot simpler, where if I can get a CPU core on here, or just something simple enough running on here to do just basic code generation, where like I turning it into a typewriter, where I am putting these PS2 codes into here, decoding that, and printing out ASCII codes through this UART. And just as simple as that. Just sort of doing a pass through and seeing what it's going to take to do that. So we'll experiment and see what we can do here. So if you check out the description, of course, I have a link to the repository of that I forked that has all of these demos that you saw in there, including the new one that I created for the Digit Tube. You'll be able to get all of that on there. But if you really want to be right in the thick of what I'm doing and be able to have an even closer connection to me, and a really a way to contribute to what you see on this channel, and provide really invaluable feedback before these videos come out to the public, either click that join button like you saw before, or better yet, come on Patreon, where most of the folks are hanging out. And these folks here get to see all of my videos well before they go public, and give me some of that early feedback, and can really also get really engaged about doing a lot of this retro development, and follow me on this path of taking this crazy thing off of Wish and making it into a single board computer. So please, and if you haven't done any of that yet, like, comment, and subscribe, but especially subscribe to my channel. That's what tells YouTube that you like what I have to offer, and that you want to see more of it coming up for you. And you click that bell to be notified, and you'll see immediately when I post another video. And of course, all of that part is free. So thanks again, and I'll talk to you again soon. Bye-bye.